Sorry. So I am Andriy Kharchenko, a software developer representing a data science group at Excel Informatics and the National Center of Advanced Translational Science. I would like to present Nyxus, our new image measurement software that can be smoothly integrated into existing machine learning pipelines, speeding up screening massive data sets of microscopy images of various types. So, so the biggest motivation for this work is the existence of high content screening techniques, where phenotype changes need to be detected and measured. So I just reminding that HCS is the cell-based quantification of several processes simultaneously, providing a detailed representation of cellular response to biochemical perturbations. So a typical HCS workflow is presented on the right, and this workflow generates a huge amount of data, images that need to be analyzed by some automatic software. So on this slide, let me give you a picture of data that we deal with at Excel in context of the HCS and beyond. So we work with the segmentation mask intensity paradigm. The segmentation task is typically taken care by separate software in the pipeline. So type 1 data sets, like on the left, is tens or thousands of relatively small or emissive images having relatively little amount of arrays, regions of interest. In contrast, type 2 on the right, large whole slide scans usually coming as tiled or emissives. So they typically contain hundreds of thousands of regions of interest. And segmentation software is capable to find region arrays shared by adjacent tiles, which presents additional difficulty for feature calculation. Typical array mask is below. This is another example of images we deal. Meeting a requirement of being multi-purpose, we sometimes need Nyxus to process even larger intensity TIFF files with large arrays sharing many TIFF tiles, and often after artifact corrections and alignment, like in the Legali paper. And alignment and the order comes in the metadata. So as mainly HCS data analysis software developers, but also needing to process legacy data, we'd like to have just one feature calculator, and we have several conflicting requirements. We need to process huge images, so no RAM related issues, buffer overruns, hash tables, problems with lookup tables with huge data are allowed. We need an ability to merge regions of interest and work very fast. meaning scan tile TIFFs fast, do summary calculations fast, preferably able to operate as an Amazon node, command line utility, and implement a rich number of features. So we, of course, there are several great tools that are not in this comparison chart for some specific reasons. For some of them are more for interactive scenarios, like IMEA, Pyrodynamics. Cell Profiler is also a great tool, but does not meet the image size and speed requirements. So these are the kind of pre-existing Nyxus competitors. Main problem of them is support of huge images. Nyxus. Nyxus is a newly built instrument, and as a newly built piece of software with a series of modern software best practices in mind, it outperforms the previously mentioned competitors, and of course has its own limitations, like it implements less features than Cell Profiler, and especially the 3D voxels. But it's high performing, and image feature base is rapidly growing. So let me show you the architectures behind Nyxus performance. So the architecture is a sequence, just a sequence of blocks, some sequential, some parallel, addressing specific bottleneck. So bottleneck number one, typically low speed of loading large tiled TIFF files. Bottleneck two, search operations, for example, between ROI, finding ROI neighbors or calculating media. And number three, everything involving co-occurrence matrix operations is pretty slow on CPU machines. So this architecture addresses all the mentioned bottlenecks. So we have a high performance TIFF scanner, multi-core and the GPU blocks, and data structures to handle shared ROI, accumulating data from different tiles, and online estimators of some simple features and statistics, like, for example, pixel intensity statistics. The output is typically to CSV files. Here we have three independent zones of parallelism. The task of feature calculation permits three zones. Zone one, physical image file loader, which is a relatively low-level kind of programming. The idea is to load a chunk of image in RAM with the biggest cache possible, let the pixel scanning algorithm do its work, and while it is still doing its work, freeing cache, preload the next chunk. Second zone, operations within a tile, pixel operations. It can scale when a tile becomes huge, really huge. And grid blocks, relatively independent groups of features consuming common data, these arguments. This can be parallelizable by unique ROI label. So it's possible. This existing of these three zones is natural to the whole feature extraction calculation problem, and it gives us freedom to tune performance. For example, we have a an 8-core machine for this, so we can give 2 cores for image loader, run pixel analysis in main thread, and let reducers consume rest for 6 cores. Or in contrast, we can have a huge image but relatively low number of ROI, so we can give most of resource to the low-level scanner. Next slide. Quick remark on the tile scanner. I mentioned that it's able to preload chunks of image while we do our analysis on the previously loaded portion. This just involves this symmetric kind of 2-section logic, which is both beneficial on in scenario number 1, when we have many primitive images, or just one whole slide image. Next kind of blocks of the architecture, which permits merging and analyzing a huge ROI. One thing that is interesting about this kind of block is using online estimators as much as possible to relieve reducers from the need to perform some trivial calculations. So this is basically after the Welford idea, and the graphs show how quickly online statistics are or estimators approach the ground truth. Last block is just massive calculations of features. So what is special about this block? It is configurable for just plain workstation like one notebook, or can be deployable on a Amazon Web Services HPC node, especially if a node has NVIDIA link, just creating huge GPU resource. So multiple deployments are possible. Wrapping up, ongoing developments. We are intensely using GPU if it is present in a system for coherence.
You have 1 minute. Thank you.
Yes, wrapping up. Yeah, intensely using a GPU for calculating features where requiring large matrix operations. So the remarks above and in the bottom of this diagram are names of feature methods and sometimes feature groups, just reflecting what features are calculated by each architecture block. And one of the interesting ongoing directions is we are adding Python interface. Actually, it exists for some basic features to enable reproducible work with this instrument. So Nyxus can be used as a high-performance utility, and if some data scientist wants to play with specific features, it can be calculated from Python. Just wrapping up summary, high performance optimized modern feature calculator, distributed arrays, relatively rich feature set. At the moment, it's around 250 features, deployable on many platforms, PC, Linux Workstation, Cloud Node. Thank you.